Okay, I'm recording. I think it must ask you if you want to continue with the recording.
Yes, I receive a message and yeah, I continue
Okay,
with call. Okay.
okay. So yeah, I'm gonna start and share my screen with you.
Yes.
Can you see my slides?
Yes, I can see it.
Okay, and can you see my pointer on the slide?
Yes.
Okay, so today what we're gonna do is to record this lecture, this online lecture for the African School of Physics. The first time I delivered it, for some technical reason, we could not record it. So today I'm doing that with Can, who is my current PhD student. So it's about a theoretical introduction to physics beyond the standard model, but from an experimentalist point of view. Okay, here is a slide of my short bio, but since I have a lot of material, I will just skip that and let you read that at your own pace. So let's jump to the outline of the lecture. Two parts, one about the standard model of particle physics, its building blocks, some recaps of the main results, and then once all of that is reminded, we will discuss about its successes and its limitations. Because there are still open questions, the limitation of the standard model are a good incentive to try and go beyond. That's the second part. And there are many models going beyond the standard model, but today I chose to describe different models, three first: grand unification, extra dimension, supersymmetry, which are by themselves good possible extensions of the standard model. And then in the end, superstring that somehow uses features common to the three first. So let's start with the first part, reminders about the standard model of particle physics. So as all quantum field theory, the standard model is defined by its particle contents and its symmetries. So the particle content is described here on the left-hand table. You have the different particles, quarks in purple, leptons in green, the gauge boson in orange, and then the Higgs boson in yellow. We will come back to all of these type of particles. Here, for example, one of the property of the particle, the electric charge, can be explained in terms of the quantum number, and here T3 is the third component of the weak isospin, and Y is the weak hypercharge. This theory, and I will describe also this in detail, does not have anomaly, and it is renormalizable. In terms of symmetry, there are symmetries of space and time contained in the Poincaré group. It is the Lorentz group with the rotation and boost in space-time. To that, if you add a translation in space-time, then you have the Poincaré group. The standard model also obeys invariance under the product of discrete symmetries, CPT. C stands for charge conjugation. This would transform a particle into an antiparticle. P is space reversal, where you change the sign of the space coordinate. And if you do the same with time, then you have T, which is time reversal. And then there are internal quantum symmetries, which are contained in the gauge group of the standard model, which is SU3. essentially for strong interaction, SU2 for weak interaction, and U1 more or less for EM interactions. Okay, so the standard model is the theory describing all known elementary particles and explain their interactions except for gravity. Formally, it's a relativistic quantum field theory, and therefore it complies simultaneously with special relativity and quantum mechanics. Symmetries play a crucial role, not only for the classification of the diverse particles, but also to understand their interactions. And formally, it's a part of mathematics which is called group theory, and especially Lie groups, which are used to this end. Here at the bottom, I show you two examples of the use of group theory. One for classification, it is the eightfold way, which enables to classify the different hadrons based upon their quark content using the SU3 flavor symmetry. And there you can, for example, describe the different mesons or the baryons in the different representation of this group. I don't go into the details here. And you might also use the symmetries for the dynamics. And this relation between the symmetry and the dynamics of the systems are ensured by the Noether theorem, which states that for any continuous symmetry, you have a conserved charge or a conserved current. There are different examples here. For example, if you have a system, a physical system, which is invariant under translation in space, it means that the linear momentum of this system is conserved. If, for example, a system is invariant with respect to translation in time, then it means that energy is conserved for this system. Let's discuss about spin. So the symmetries of special relativity, the Poincaré group, show that elementary particles can be labeled by their mass and spin. Spin for massive particle and just helicity for massless particles. And depending on their spins, particles can be divided into two classes. So the fermions, which have half integer spin, and the bosons, who have integer spin. So for the fermions, they obey the Fermi-Dirac statistics, and they have an individualistic behavior. You know from your previous studies that the Pauli exclusion principle states that two electrons cannot occupy the same quantum states. Therefore, for two electrons to sit in the same atomic orbitals, they need to have opposite spin. The type of particles described here are ordinary matter particles like electrons and quarks who have spin 1/2. On the other hand, the boson obey Bose-Einstein statistics, and they have a gregarious behavior, like, for example, photons in laser that can gather very numerously in the same quantum state. The elementary particle having this type of behavior are the vector bosons with spin 1, gluons, WZs, and photon. And then there is a special class of boson, which are scalar boson with spin 0, like the Higgs boson. Okay, let's do just two interludes that will be useful for the rest of the presentation. The first one is what I call quantum mechanical lenses. Exploring matter at very small scales requires to use three separate magnifying lenses. And these lenses are direct consequences of quantum mechanics. So first of all, you know that quantum mechanics is probabilistics, and therefore you need what I call a statistical lens. It means that you need to repeat measurements many times so as to measure the central value of a certain quantity with sufficient precision. Also, you know that you can express quantum mechanics via wave mechanics, and all particles have both corpuscle and wave properties. All particles are associated with a wave, which has the de Broglie wavelength, which is this lambda defined by h over p. Since h is a constant, you understand that if you want to probe matter at small scales, you need high momenta, therefore somehow a high energy lens. And then there is a third one, which is required when you want to have an accurate theory prediction, which is what I call the quantum lens. So also, you know that in quantum mechanics, seldom physics cases have an exact solution. And usually we use approximate methods, often perturbative expansion. Here I give the example of scattering amplitudes for the production of a W at a Hadron Collider, for example, at the LHC. You have a first term, which is a leading order, then a second term, which is these correction to the first term with real emissions and virtual emissions. And all that comes, the successive terms come with the power of a coupling constant. And here we directly see that if this coupling constant is small, small with respect to 1, then the power of this coupling constant will make this factor very small, and the series will converge rapidly. On the contrary, if you have a large an order 1 coupling constant, then you'll need to calculate many terms in order to have a good approximation of the process. Let's go to the second interlude, which regards the space and time symmetries. So these, as I mentioned already, constitute the Poincaré group, which contains the Lorentz group, form of the boost and rotations in space-time. To that, we add translation in space-time, and we get the Poincaré group. The Lie algebra of this group writes with these different commutating relation. So commutation between the 4 momenta, or the 4 momenta and also the generator for boost and rotation, which are these mu nu matrices here. These have so-called Casimir operators. The Casimir operator for Lie algebra is an operator which commutes with all the generators of this algebra. And here, for example, you can take p squared, which is equal to m squared, and this commutes with the p mu and the m mu nus. There is also a vector down here, which is called the Pauli-Lubansky vector, which square is also a Casimir operator commutating with the p mu's and the m mu's. And so this makes two quantities invariant in the Poincaré group, which is the mass related to the momentum and the spin related to the Pauli-Lubansky vector. And that's why I mentioned in the beginning that all the particles actually sit in irreducible representation of the Poincaré group, which can be labeled in terms of their mass and spin. Um, uh, I just give a few examples of different mu news matrices that we could encounter for example, boost, rotation, or discrete symmetries. So let's discuss about the particle content of the standard model. We have seen that there are fermions, and for the fermions, they obey the Dirac equation. So for example, for a single free particle of spin 1/2, let's say an electron, denoted psi, the dynamical equation that replaces the Schrodinger's equation in quantum field theory is the Dirac equation. So it's derived starting from the matter energy equivalence that you've seen written here. And Dirac has tried to linearize this equation. It's not doable with ordinary numbers. For this, you need to introduce these alpha and beta matrices under this form. And if you express that using natural units, that is h bar equals c equals 1 to simplify the notation, and also redefining gamma matrices in terms of alpha and beta matrices, you can arrive to this very compact form of the equation. Here, the mu index is a space-time index that can take 4 values, 1, 2, 3 for x, y, and z, and 0 for the time coordinate. To this Dirac equation corresponds Lagrangian density that can be written like this in terms of the psi, represented, for example, the electron with its mass m here, and this would be the positron in this Lagrangian. Okay, here is a table describing all the fermions, and these represent the matter constituent. Actually, ordinary matter is just made of the first generation of quarks and lepton that appears in these two first lines of these tables. So there is the electron with its neutrino, and there is up and down quarks. From these up and down quarks, you can construct the nucleons. From the nucleons, you can construct the nuclei. Having electrons in the field of the nuclei, you can form atoms, and with different atoms, you can construct molecules, etc., etc. So all the ordinary matter is just made of these quarks and leptons here. And for some unknown reasons, there are two replications of these particle with heavier mass, and it's not understood so far why there are these two replications of matter constituting the second and third families of fermions. About the fermions, we can discuss a special property which is called chirality. Under weak interactions, the fermions are chiral. It means that they are not the same as their mirror image. This notion was introduced to account for parity violation in weak interactions by two Chinese theorists, Li and Yang, in 1956. Since their prediction was confirmed by Mrs. Wu et al. The year later, they earned the Nobel Prize in Physics in 1957. The right-handed and left-handed fermions have different weak interactions, and therefore you can start off a fermion field represented here and decompose it in its right-handed and left-handed components by using this projector that can be expressed in terms of the gamma-5 Dirac matrix. And if you do that, you'll find that the right-handed part is an SU2 left singlet, some type of just a scalar, if you will, whereas the left-handed projection is a doublet under SU2 left, some type of vector in this type of space. And so, for example, in the mass term that we could have for the electron, in principle, you would multiply the right-handed part by the left-handed part, but doing so, you would not obtain a scalar because you would multiply just a single number with a vector, so you would get a vector, and this cannot fit in a Lagrangian, as we will see later. In particular, the consequence of the chirality is that the W boson do not couple at all to the right-handed fermions or equivalently to the left-handed antifermions. And that's why, for example, in the standard model, you don't have right-handed neutrinos or left-handed antineutrinos. The fermions can also cause so-called anomalies in the standard model. And this is in general the case in chiral quantum field theories. So the anomalies are interactions that are absent at the tree level and only appear at the quantum level through loops where the fermions can circulate. It only occurs if within these loops you have a vector which has an axial coupling, so a pseudo vector, if you will, and two other vertices with vector couplings. So for the name, you will find in the literature these anomalies called axial, triangle, or Adler-Jacquiw and Bell anomalies. These graphs, these Feynman graphs for these anomalies are divergent and non-renormalizable. And within this graph, each fermion circulating in the loop contribute irrespective to its mass. And so the only possibility to avoid the divergences here, provoking infinite scattering amplitudes, is to ensure that you have cancellation between the contribution of different fermions. So here you have a Feynman diagram showing the simplest one loop contribution to anomalies. You can see that in this vector, in this vertex here, you have gamma mu gamma phi, that means a pseudo-scalar coupling. And here you have vertex couplings. It means that here, for these two vertices, you have vector currents with the generator of a given group. And here you have an actual current. So the condition to cancel the anomalies in the standard model, for example, in the quark sector, is that you have all the axial couplings of up quarks which are equal, and at the same time exactly opposite to those of bottom quarks. And in this case, when you sum up the contribution of all the quarks to these type of diagrams, they completely cancel, leaving the standard model anomaly free. Another thing that appears in the fermion sector is mixing in different sectors. So you have mixing in the quark sector and also in the neutrino sector. What does it mean? It means that the mass eigenvalues and the interaction eigenvalues are not the same, and therefore you need a unitary matrix called V here to rotate from one to the other. This unitary matrix here for the quark mixing is called the Kabibo Kobayashi Maskawa, named after these authors here. And you have different values of this matrix element, which are measured in different experiments. The phase of this complex unitary matrix is in the standard model the only known source for CP violation. You have an equivalent phenomena for the neutrino. You have mixing in the different neutrino flavor parameterized by another unitary matrix, which is called Pontecorvo-Maki Nakagawa-Sakata matrix. And it was discovered experimentally that neutrino oscillate, and this is only possible if they have non-zero mass. Okay, now we will see how the symmetries are incorporated in the description of the elementary particles. So elementary particles are quantum fields. Here, for example, the field is denoted phi, and the physical system is represented by a scalar function, the Lagrangian, which depends on the field and its derivatives. From this, you can calculate an action by integrating over space and time a Lagrangian density, like in this formula. And then you can infer the dynamics of a system from the least action principle, where you want to maximize the action. And this means that the derivative of the action with respect to the field must vanish. If you apply some symmetry operation to your physical system, it has to leave it invariant. And it has been shown by Wigner that you can express this gauge transformation via this type of formula, where you have the T, which is the transformation generator, and theta, which is a transformation parameter. And if you do that, if it's a good symmetry, then even by changing the phi into phi prime in the field and the derivative, it should leave the Lagrangian unchanged, since it's a symmetry. And you have two classes, if you will, of such transformation. One which is called a global transformation, global symmetry. In this case, the parameter of your transformation does not depend on the space and time coordinate. Or you can have a case where the parameters depend on the space and time coordinate. And this is the way in quantum field theory that we introduce the gauge interaction via the covariant derivative, which I give an example here. So this delta mu is just the standard derivative with respect to space and time. And then if you add this portion here for weak interaction, it transforms this into a covariant derivative, introducing the weak interaction in the theory. Also, in the theory, in order to make a sensible prediction, it needs to be renormalizable. And the basic rule, if you will, can be seen from a dimensional analysis. The the mass dimension of the Lagrangian is some power of the mass, and this power needs to be less or equal to 4 for the theory to be normalizable. Okay, let's try to see an illustration of the global and the local symmetries. So let's imagine a system represented by this rectangular grid here. If you rotate that by 180 degrees, this will leave obviously the system invariant. And this is a global symmetry where all the points in the system undergo exactly the same rotation. For a local symmetry, each point of a system will undergo a different rotation, and therefore this might distort, deform the system. And in order to leave it invariant, you will need something that exactly compensates this deformation. And it can be shown formally that the compensation with respect to the system deformation is precisely the gauging interactions. Okay, let's discuss a bit more the fundamental interaction between elementary particles. You have two drawings here. At the top, the left-hand side drawing is illustrating repulsive interactions. You have two small boats here, and every time boson is exchanged in this interaction, every time it's thrown or received, the two boats will move away from each other. On the right-hand side drawing, it's the reverse situation where you have an attractive interactions. Every time this object is thrown or received, it will move the two small boats closer from each other, like it would result in attractive interactions. So here I list the three fundamental interactions that are described by the standard model. Electromagnetism, it was the prototype quantum field theory known as quantum electrodynamics that was first built in the 1940s to describe this. It's based on an abelian symmetry group, U1 electromagnetism, which has just a single generator that corresponds to the photon particle with spin 1. The photon couples to electric charge. The range of the interaction here is infinite. And if we set the intensity of the strong interaction as the reference, you can see that the intensity of electromagnetic interaction is a few orders of magnitude less. The electromagnetic interactions are responsible for the cohesion of matter at the atomic and molecular level, which are based essentially on the attraction between the electrons and the nuclei in these physical systems. The strong interaction has also quantum field theory describing it, which is called quantum chromodynamics. It's based on a non-abelian symmetry group, which is SU3C for color. This has 8 generators, which correspond to the 8 different gluons, which has spin 1. And the gluon coupled to a color charge that can take 3 values that we can set to red, blue, and green, if you will. And the gluons bear themselves color and anti-color charge, so they are subject to self-interactions. The range for this interaction is very small, the order of 1 Fermi. And this is responsible for the cohesion of matter at the scale of the nucleon or the nucleus. And then you have weak interactions, which are described by the electroic theory. here it's based on non-abelian symmetry group, which is SU2 left. The left symbol here is meant to remind that this interaction is chiral. This has three generators corresponding to W plus, W minus, and Z, all particle with spin 1. And the weak gauge boson coupled to weak hypercharge, and they are also subject to self-interactions. So W's and Z couple differently, as we mentioned already, to left-handed and right-handed fermions. This is the results of their violation of parity. The range of this interaction is very small, and its intensity is also very, very weak, uh, really orders of magnitude weaker than strong interactions, for example. And the weak interactions are responsible for beta decays, for example. And then there is one interaction which is not described by the standard model, which is gravitation. At the level of elementary particle, it's essentially negligible. So it's actually not treated at all in the standard model. And anyhow, we do not have a good quantum theory of gravity as of now. If we had, we suppose that the carrier of this interaction would be the graviton with spin 2. The range would be infinite, and the relative intensity at low energy will be really extremely weak, really almost 40 orders of magnitude weaker than the strong interactions. But this would be responsible for the cohesion of matter at very large scales, at the scale of the solar system, galaxies, clusters, or even larger structures. You know that we do have a classical theory for this interaction due to Newton. And here the force is exerted instantaneously, irrespective of the distance. And this is, of course, in conflict with special relativity. In 1915, Einstein made a theory of general relativity, where you have local matter and energy density that actually deform space-time locally. And the trajectory of the bodies are still geodesic, but in a deformed geometry of space-time. This is depicted here, where you do have a body coming close, for example, to a very massive star, and which trajectory is deflected just because it falls into this deformed geometry close to the location of the massive star. This is a theory based on invariance with respect to local change of coordinates. So it is a gauge theory, but a geometrical gauge theory. It's not quantized. Okay, so now we will see the different equations that applies to the boson. So in the case of an abelian theory, we have quantum electrodynamics with the photon as a carrier of this interaction. The photon doesn't have an electric charge, so it doesn't have self-interactions. And it obeys the Maxwell equation that you can describe in this way in a covariant formalism, where you have here this F mu nu, which is the electromagnetic field strength tensor, defined this way as with respect to derivative, space-time derivative of this quantity here, which is the four vector, the four potential, which is the ordinary vector potential that you have in classical electromagnetism, and this is equal to the four current, which is described this way, with the ordinary current in classical electromagnetism and the charge density. And this is, of course, phi here, the scalar potential that you have in classical electromagnetism. The Lagrangian of these EM interactions, when you place, for example, a charged particle in an electromagnetic field, is given by this quantity here. If you have a non-abelian case for the gauge boson, like for example WZs or gluons, these vector bosons are subject to self-interactions because they are described by non-abelian theory, and you have the Young-Mills equations that you can see here, where the field strength tensor F mu nu can be described in terms of the gauge boson, the generator, and the covariant derivative that you can see here. The Lagrangian will be the trace of this product divided by a so-called Dynkin index, which is some kind of normalization between the generators of the group describing this interaction. Okay, here you have a table with different gauge bosons. The photons for electromagnetism, the gluons for strong interaction, and the W and the Z for weak interactions. What you can notice from this table is that all of these particles with spin 1 have a very different mass. Photon and gluons are massless, whereas W and Z boson are quite massive. So let's examine the consequence of applying the exact gauge symmetries that I've described. In the standard model, the masses of most of the particles are protected from large quantum corrections by some kind of symmetries. If you were, for example, in the Lagrangian of the standard model, to include a mass, an explicit mass term for the gluon, this would make the Lagrangian no longer invariant under SU3 of color. So therefore, if you want to respect these gauge invariants, you need to leave the gluons massless. The same applies for the photon with respect to U1 electromagnetism, and the same applies for the W and Z boson with respect to SU2 left. And on top of that, the chirality of the fermions, as I explained in the case of the electron, prevents from writing a mass term, which should be a scalar that you cannot form for chiral fermion in the standard model. The net consequence of this, as you can see, is that in order to respect these symmetries that enable first the classification of the different particles, but also the description of their fundamental interactions, you need to leave all the elementary particles massless. And we know that this is impossible. And so let's try to understand this problem or apparent contradiction. For this, what we will do is to try to estimate the range of the different fundamental interactions. You can use for this this Heisenberg inequality, you can plug in the mass equivalence relation here coming from special relativity. Why do we do this? Because you remember the two plots that I've shown before, describing in quantum field theory the elementary interaction as an exchange of vector bosons. If you do that, you can suppose that these vector bosons have a given mass, and um, they can um, they can be exchanged in a given lapse of time, and at most they will travel to the speed of light. So it means that the delta E here corresponds to just mc squared, the, their mass, and the delta t here should be compatible with these particles moving at most at the speed of light. And if you do that, you can derive the so-called Compton wavelength, which is h bar over mc. And since h bar and c's are constant, you can see that the range of the interaction is inversely proportional to the mass of the interaction carrier. So keeping that in mind, we can re-examine the different cases that we've encountered for the fundamental interactions. So first, U1 electromagnetism. Here the situation is fine. We have a massless photon. This is compatible with gauge invariance with respect to U1 EM. And this is also compatible with an infinite range interaction. Then you have strong interactions based on SU3 of color. It is known experimentally to be short-ranged, but this, in fact, can be explained by the large value of the coupling constant of these interactions. And by the way, historically, this is how Hideki Yukawa in 1934 made the first model of strong interaction via the exchange of a non-elementary particle, the pion, and that he predicted to be, 200 times heavier than the electron. This prediction was confirmed with the discovery of the charged pion in cosmic rays by Powell, Occhialini, and other collaborators in 1947. And it turns out that the mass of the pion is compatible with the range of the strong interaction. So here, for example, in this Feynman diagram based on non-elementary particle, there is a representation of a strong interaction between a proton and a neutron via an exchange of a neutral pion. And if you take the picture, the same picture in terms of QCD with the different colors, you can see that you can represent that with pi zero, for example, which is a combination of U or D quark with its antiparticle. And so here, even though we have an explanation which is not based directly on elementary particle, we have the hint that the short range interaction of the strong forces can be explained by the confinement, the strong intensity, if you will, of the strong interaction that will hide all of this color line within the proton, within the neutron, or within the pion at low energy. But for the weak interactions based on SU2 left, there is no such thing as a strong coupling that causes confinement. So here we are really left with the contradiction that experimentally this interaction is very short range, and the gauge invariance that would imply a null mass for the force carrier, meaning an infinite range interactions. And the reason why there is this apparent contradiction is that the level of symmetries that I've described so far, especially the one regarding SU2 left, is actually too high with respect to what nature has chosen. So for the weak interaction, we need a spontaneous symmetry breaking. And let's explain what it means. So this is the Higgs mechanism that was introduced for this in the standard model. So spontaneous symmetry breaking is a situation where you do have the equation that have a certain level of symmetry, but the actual solution to this equation does not. In this case, depending on the type of symmetry you break, for example, if it's a global symmetry, we have the Golson theorem that states that each broken generator of the symmetry introduce a massless scalar boson in the theory, which is called the Nambu-Golson boson. And so in the standard model, what is done is to introduce a doublet, this capital phi here, of a doublet under SU2 left. It's a doublet of scalar complex fields that you can decompose in the real part and imaginary part here. And since it's a scalar, so you know in quantum mechanics that a particle with spin s has s times s plus 1 states. And so a scalar particle here would have, no, sorry, two s plus 1 states. So a scalar particle here with spin 0 just represent a single degrees of freedom. And so these four components here represent in total of this doublet, represent in total 4 degrees of freedom. And we'll keep that in mind so that we can find important conclusion of this Higgs mechanism in a few slides. So once you have these doublets, you associate it to it Lagrangian, which is this part here, the kinetic energy of the Higgs doublet and a potential. The covariant derivative that you include here can be described like this, with the ordinary derivative and additional terms related to U1 and SU2 type of interactions. The potential can be, in order to be renormalizable and respect the different symmetries, can have this general form, lambda phi to the 4 plus mu squared phi to the second power. Obviously, you need a positive lambda, otherwise this potential will be unbounded from 0, which means that it won't have a minimum. And if you have this lambda positive and mu squared positive, then you simply have, in projection, for example, here, some time of parabola with a trivial minimum here. On the contrary, if you have opposite signs, that means mu squared negative, you have this Mexican hat shape for the Higgs potential, which triggers a spontaneous breaking of the electroweak symmetry. Why is that? So here you would have the Lagrangian that still keeps its rotational symmetries with respect to this vertical axis, whereas the solution, which is depicted by the angle chosen by this blue marble to fall down at the minimum of the potential under some small fluctuation, that will choose, so all the angles of the fall are completely equivalent. So this is the level of symmetry of the equation. But the solution will pick a specific angle and therefore break this symmetry. And you can find a non-vanishing expectation value of this field expressed this way, which is where V here is this vacuum expectation value that is expressed in terms of the parameters of the Higgs potential. Okay. Now, if you look at the potential, there are actually three quanta of rotation of the smiley here along this circle at the minimum of the potential, which corresponds to Nambu-Goldstone boson, which will be eaten by longitudinal component of W and Z's to give them their mass. And if you examine this in terms of potential, this Goldstone boson always stays at the minimum of the potential, so it costs no energy to circulate around this circle. Since it costs no energy, this corresponds to massless modes as it was imposed by the Goldstone theorem. On the other hand, if you look at the oscillations up and down the minimum of the potential here, since you climb the potential here, it has a cost in energy, and therefore this corresponds to a massive mode. And in case at high energy or high temperature, where you do have the mu squared, which turns to be positive again, like the lambda parameter, then you no longer have this Mexican hat potential and just have at this place a trivial minimum of the potential. And in this case, the electroweak symmetry will be restored. It means that it would be apparent and no longer hidden, as we have the case at low energy. So before the spontaneous breaking of the electroweak symmetry, all the particles in the standard model are massless. After this symmetry breaking, the particle acquire their mass via their interaction with the Higgs fields. And in other words, we can say that the Higgs boson coupled to the mass of the particle. And there are different types of interactions for this coupling. For example, there are a weak interaction between the Higgs fields and the W's and Z. So via this, the weak coupling constant and the vacuum expectation value of the Higgs, the W acquires a mass, the Z acquires a mass also. There is no interaction between the Higgs field and the photon, which leaves the photon massless. Since SU2 is non-abelian, the Higgs boson has self-interactions that explain its own mass. And you can express it, for example, in terms of the mu squared parameter. The gluons don't have quantum numbers under the electroweak part of the theory. Therefore, the gluon does not interact with the Higgs field and it leaves its mass equals to 0. And the fermions in the standard model can interact with the Higgs fields and acquire their mass via this Yukawa coupling, which are not predicted by the theory, but can give a mass to the different fermions. Now, if we look at the accounting of the number of degrees of freedom, So we have introduced with the SU2 doublets of complex scalar field 4 degrees of freedom in total. 3 of them are eaten to give a mass to W plus, W minus, and Z. So there is 1 remaining degrees of freedom that corresponds to the physical Higgs boson. I will just skip this slide. This is just to illustrate uh, the uh, how the coupling constant equalize in interaction between electromagnetism and the weak force, but I will just skip that. For the scalars like the Higgs boson, it's the Klein-Gordon equation that applies in quantum field theory. And this is just constructed based on the matter energy equivalence using the correspondence principle, and you get this equation here. And for example, the Higgs fields obeys to this equation. So we have gone through some recaps about the standard model, excuse me, and the most important success of the standard model was, of course, the discovery of the Higgs boson announced in 2012 at CERN, and that was discovered by the ATLAS and CMS experiment. The standard model has also lots of successes because all the measurement about the elementary particles essentially are explained by the standard model. In particular, even if you do really precision measurement on different observables here in the, for example, the Higgs mass, the Z width, excuse me, a few asymmetries like backward, forward asymmetries, the top mass, the measurement of coupling constants, etc. You compare that to calculation based on state-of-the-art theory, and what you can see is that for the most part, we have a very good agreement between the prediction and the measured value, and you have just a few tensions which are less than 2.5 sigma. So overall, very good agreement. Um, and if you look in particular at the Higgs, at the couplings of the Higgs bosons, so here you have on the vertical axis the couplings of the Higgs boson with respect to fermions, with a kappa factor here that can be adjusted in a fit, and the square root of kappa v here for the coupling to vector boson that can also be adjusted in the fit. And you can see that you measure actually what is predicted by the model. If you do the ratio plot here, you will find directly kappa f and square root of kappa v, and you can see that everything is happening as predicted in the standard model. Okay, so this looks fine and explains lots of phenomena that were observed for elementary particles, but still the standard model does not explain everything. It has limitations. First of all, it has 26 unpredicted parameters in total, 19 general for the gauge couplings, the Yukawa couplings, which are not predicted, the parameters of the Higgs potential, the 3 elements plus the phase of the CKA matrix. You could even have these theta PC angle parameter, sorry, which is related to possible CP violation, the QCD Lagrangian. This is called the strong CP problem, plus 7 parameters that you would need to parameterize the non-zero mass of the neutrinos. So having all of these 3 parameters somehow illustrates the limitation of our understanding, and the consequence is that you lose predictivity, intrinsic predictivity of your model. You can somehow regroup these limitations of the standard model in different categories. You have, for example, the flavor problem, the unification problem, and problem related to the dark universe. So for the flavor problems, we don't know why there are 3 generations of fermions. We can ask, for example, if the quarks and leptons are really elementary particles, or if they could be composite. We don't know what is the origin of the CP violation. And there is also a puzzle that the CP violation from the CKM matrix is insufficient to explain the baryon asymmetry that we observed in the universe today. So for the unification problems, for example, we don't know how to stabilize the Higgs boson mass in presence of a high scale. For example, we don't have a quantum theory for gravity, etc., etc. So there are a certain number of things, like, for example, the quantization of the electric charge, which are not explained by the standard model. And then for the dark universe, as you know, neither dark matter or dark energy can be explained in the standard model. Just to describe a bit more the stability of the Higgs mass. So here, imagine just having a free Higgs propagator here, which would be just this dashed line. At the one loop level, you might have corrections to this propagator with loops within which fermion can circulate, but also gauge bosons or the Higgs boson itself. And here, for example, for the fermions, so it's essentially the top, which has the largest contribution, since it had a Yukawa coupling of order 1. Here, if you look at the mass squared of the Higgs boson, corrected at the one loop, it's the bare mass of the Higgs boson squared plus this quantity here, where you can see contribution from the different boson that circulate in these loops, and also contribution from the top quark loop. And what you notice also is that these loops have bosons circulating in the loop, and they have positive contribution, whereas the top loop has fermions circulating, and these have a negative sign. And so the Higgs mass diverges quadratically with respect to lambda, and here lambda is the cutoff scale. So it's the physical scale at which this description fails. And so here you have in presence, for example, of a fundamental energy scale, the Higgs mass, which is destabilized by this quadratic divergence. And so there is no guarantee to keep it at the electroic range, like, for example, unitarity would require. For this, let's take the example of a grand unification where you have this lambda up to 10 to the 16th GeV. You would need to fine tune the different parameters appearing here in order to have this renormalized mass which is 125 GeV squared. You would need to adjust these parameters with really inelegant fine tuning, and you would need to repeat this at 2-loop, 3-loop level, etc. So this is just an aesthetic problem, if you will, but still it makes people uneasy about it. So all the limitation of the standard model that we have seen rapidly are incentive to try and fix the open problems by going beyond the standard model. And here you have the identikit of the standard model with its gauge group, the space-time symmetry, the number of space dimension, etc., the mechanism that breaks electroweak symmetry. And you can take each of these feature and think of extending, for example, the gauge group to having a larger gauge group. The space and time symmetry, you can, for example, introduce supersymmetry, the number of space dimension, and you go to model with extra dimension. Instead of having the Higgs mechanism, you can imagine a strong breaking of the electroweak symmetry. You can introduce more leptons, for example, a fourth generation, or think that the quarks and leptons are a composite object. And of course, you could possibly also combine different type of such hypotheses to construct an extension of the standard model. So now we move to the second part with an extension of the standard model, and we will start with extra space dimension. So the first attempt for theory with extra space dimension was due to Nordstrom in 1914. It was an attempt to unify Newtonian gravity with electromagnetism, which did not had much success and attract much attention. The next year, Einstein has developed his theory of general relativity that I already spoke about. And a few years later, it was starting from this theory of gravity that Kaluza tried to unify it with electromagnetism by extending the metric tensor of four-dimensional Minkowski space-time, which is this J mu nu here. He added a term here of diagonal related to electromagnetism, and then there is an additional diagonal term, which is called sometimes the radian. And in this model, five-dimensional gravity is seen in four-dimensional space and time as gravity plus electromagnetism. In 1926, Oscar Klein made a quantum version of Kaluza theory and also find a good physical justification of the very small size of the fifth dimension. So, of course, Kaluza figured that the extra dimension should be small and probably too small to be measured, but had no good justification for this. Klein found a justification saying that if we had a quantum theory of gravity, then dimensional analysis show that the mass scale should be the so-called Planck mass, and related to this, the length would be the Planck length, which is extremely small. And this would be a good reason why we don't see this extra dimension, because they are too small to be experimentally probed. But all of this construction leads to phenomenological problems with massive fermions or bosons that they cannot explain. So for a long time, for a few decades, they were somehow forgotten about. And it was in 1995 when Ed Witten showed that 11-dimensional supergravity is a low energy limit of some superstring theory, that this renewed interest in theory with extra space dimensions. So in this type of models, you have a few constraints coming from Newtonian gravity that you still need to respect when it was, where it was precisely measured. And in general, the modification of the Newtonian potential is parameterized this way. So this, here you recognize the classical potential, and it's modified by this term here. And for example, if you have a compactification of the extra dimension on a two torus, you will find, for example, these values for these two parameters. So depending on the number of parameters here, you have you need the size of your extra dimension with different constraints here. And for example, since gravity is measured down to a few tenths of microns, this excludes the cases where you would have just one or two extra dimensions here, which are ruled out by this constraint. In 1998, Nimar Kanyamed, Savas Dimopoulos, and George Valley proposed a model that could explain the hierarchy problem. So the idea here was to introduce several extra dimensions, and only gravity could propagate in this extra dimension. So the geometry was that of the fourth dimensional Minkowski space, plus associated to each point of the space and time different circles with extra dimension. If you express the Gauss law in this, you would find an apparent Planck mass here that depends on the actual Planck's mass with powers of the radius of extra dimension here. And the idea was to take this apparent Planck mass down to the electroweak scale, and therefore they needed either numerous or and large extra dimension. And in this case, gravity would naturally appear weak in 4 dimension because part of its flux would go into the extra dimension. In order to compactify, to keep these extra dimension very small, they are periodic. So for example, if you have just one extra dimension, this y coordinate here, you have this periodicity condition here that you also apply in the field. And so the Fourier expansion that will transform this position condition on momentum space will give you here decomposition in a tower of different states with this mass. And if the extra dimension are really large, then you have a quasi-continuum of these different states with different Kaluza-Klein excitations like this. The signature of these ADD models are, for example, real production of gravitons at colliders, E plus E minus or PP. So here, for example, you have Feynman diagrams to produce a graviton at the LHC, for example, whereas here it's produced in a E plus E minus collider. The graviton couples to the energy momentum tensor, so it would essentially couple to all particles, gluons, photons, whatever. And here, for example, you could have a signature with a monophoton where the graviton would escape in extra dimension. And so you would be left here with a photon plus nothing recoiling against this photon. And so this is a typical signature of extra dimension. It would be the same, for example, here with a monojet produced by this gluon or quark at the LHC. You can also have a virtual exchange of gravitons, like depicted in this Feynman diagram. And so this would modify difermion distributions here, or dibosons distribution. So here you would have, for example, dilepton production at the LHC, plus an additional contribution with a graviton, a virtual graviton exchange here. And since here you have the same initial and final states, these two amplitudes are completely compatible, so they interfere. And then on top of that, you would have, for example, a gluon contributions with a graviton exchange that will add up to this cross-section. So you can parameterize the double differential cross-section for this type of processes with a contribution from the standard model, an interference term coming from this part here, and then this additional bit coming in here. And so if you do precision measurement of your differential cross-section for, like, for example, for dileptons or diphotons, you can try to probe the presence of extra dimension as planned in the ADD model. There is also another model of extra dimension that had attracted a lot of attention. It is a model with a small, highly curved fifth dimension introduced through a warped geometry. So here the geometry is that of an anti-de Sitter space with this metric here, and you can see that there is a strong reduction factor of the metric here. And this K factor here is the curvature scale. In our word would be on a brain here, and there would be a gravity brain where the gravity would be strong, and because of this warp factor here, gravity would be seen quite weak in our usual world. Typical signature of that would be sharp resonances of a spin-2 particle, and this is the Randall syndrome model. So extra dimension, in summary, what type of open problem could they solve? Well, they could solve the hierarchy problems. So meaning that there are orders of magnitude between the electroweak scale and the Planck scale. Here, the effective Planck scale would be driven down the TeV, therefore alleviating the hierarchy problem. And there would be also the explanation why gravity seems really so different, almost 40 orders of magnitude weaker than strong interaction based on the special geometry. Um, and what would be the signature of such um, theory? We have seen single production of different objects, monophoton, monojets, mono weak boson. You could have modification of mass or angular spectra due to virtual graviton exchange in diphoton, dilepton, or dijet or diboson topology, and there are a couple of others that I did not describe here, the radion or the production and evaporation of mini black holes. Let's go to the next theory, which is grand unified theory. So the idea here is to try to find an extension of the gauge group of the standard model that would unify a strong interaction with the electroweak interactions. So in 1974, Georgia and Glashow tried to do that using SU5 as a gauge group. So they looked at a larger gauge group to embed the standard model. And so the rank, they looked at the rank of the different models, and it can, the rank, for example, is the number of generators that can be diagonalized simultaneously. And for example, for an SUN group, it's n minus 1, and for UN it's just n. So based on that, if you look at the rank of the standard model, you would find 4. And so they needed a group with rank at least 4 to embed the standard model. They also needed a group where you would have a complex representation, where you could place separately the right-handed and left-handed fermions in order to respect chirality, which is something important for the weak interaction, as we have seen. In SU5, you have n squared minus 1, which is 24 generators. And you can place the different quarks and leptons of the standard model in, for example, the 5-dimensional fundamental representation of SU5 here. So this, for example, corresponds to the electron and its neutrino, and here a down quark with 3 different colors. And you can place in other representation the leptons and the quarks of the standard model in this decomposition of the irreducible representation of SU5. On top of this, the quantum numbers that you have in this model would make it anomaly free, meaning that as in the standard model, you would have compensation between the different fermions contributing to the anomalies. For the gauge boson, they sit in the adjoint representation of SU5, which has dimension 24. So in there, you can place the 8 gluons of the standard model, the 3 weak vector boson, W plus, W minus, and Z, the gauge boson of electromagnetism, and on top of that, you introduce 12 new boson, denoted X and Y here, which are leptoquarks. They are called so because they are charged under both SU2 left and SU3 color. They have fractional electric and color charges defined like this. And they introduce new interaction that do not conserve separately the baryon number or the lepton number, even though they still conserve B minus L. quantum number. So here, for example, you have a representation of an adjoint representation of SU5, where you do have these leptoquarks here, these blocks here, and the different boson, I mean, the different components of the fields, like this B corresponding to U1Y, or this W3, which is the third component of the weak isospin, etc., etc. And then you also have bits of the gluon fields here. Here you can explain, for example, charge quantization. You can express, for example, this operator giving you the electric charge based on this quantum number. And if you apply this, you have this operator which is traceless, and this introduces a special relation between the charge. For example, if you remember this 5-bar representation here, you apply this traceless electric charge operator, and so you will have a relation between the electric charge of the down quark and the of the positron, whereas in the standard model it's not explained. You have evolution of the gauge couplings, and these are due to the fact that the different interaction polarize the quantum vacuum in a special way. For example, in a abelian gauge group theory like QED, if you have a bare charge here, you know from the Heisenberg inequality that in the quantum vacuum, pairs of particles and antiparticles can pop up um, uh, in the constraint of this Heisenberg inequality. And this pair of particle and antiparticle that appear in the quantum vacuum will be polarized by this negative charge here in the center. So you would have dipoles here with all the positive charge closer to the bare electron charge here. And the net effect of that is that if you are at distance, you will not probe directly the bare mass of the electron, but you will also get the screening effect of these polarized dipoles. It means that the electromagnetic interaction just described at the tree level by this photon exchange will also be corrected at the one loop level by this pair of electron positron popping up in the vacuum and contributing to this screening effect. And these, depending on the energy, will make the coupling constant associated with this interaction vary. And here it's the inverse of this coupling constant that you can see in red in this plot. For the strong interaction, for example, the same type of screening phenomena occurs here with this virtual exchange of quark-antiquarks that corrects this gluon propagator, but you also have an anti-screening effect where you have a loop with a gluon, since it's a non-abelian theory, and it's really the combination of the screening and anti-screening effect that explains the evolution with energy of the coupling constant of the strong interaction, and the same appears for weak interactions. So the gauge coupling at one loop in general for an SUN theory, you have a beta function. So the evolution of this coupling constant with respect to the log of the renormalization scale. So it's essentially the evolution with the energy scale, which depends on contribution um, in the loop by the different gauge boson and the different number of generation of fermions. So if we express that for the different part of the gauge group of the standard model, you have the evolution of the strong coupling constant here, which is related to the different contribution of the gluons, the three generator of quarks that gives you this shape for the beta function. You have a different one for the weak interactions. And here, for example, you also have a contribution of Higgs loops. And it's the same for U on Y. And so once you know the beta function of these three different parts explaining three different um, gauge interactions, you can try to fix a condition at a large energy scale where each of these different coupling constant will be equal. And from this, you can calculate the energy scale here corresponding to this grand unification, and you'll find something of the order of 10 to the 10 to the 16th or 10 to the 15th GeV. And on top of this, you can have the mixing between the weak and the electromagnetic interactions, which can be predicted by the Krebs-Gordon coefficient related to the the gauge group that you have for your grand unification. And so for example, in SU5, you can predict that the sine squared theta at the gut scale would be 3.8, and then you would just need to use the renormalization group equation to run then down to the low energy and compare this prediction to measurement. Now, of course, if you have a larger symmetry, you also need to break this symmetry. And for example, in SU5, you have a 24-dimensional Higgs multiplet, denoted like this, that spontaneously breaks SU5 and gives mass to the leptoquarks, masses of the order of the grand unification via the VEV of these Higgs multiplet, exactly like the W and Z in the standard model, as we have seen. And also, in addition to the breakup of SU5, you will still need at the weak scale to break SU2 cross U1. And you would do that with 5-dimensional Higgs multiplets here that contains, for example, a colored triplet and then a Higgs doublet that can, exactly as in the standard model, provide a mass to W and Z boson via its vacuum expectation value. And now if you look, for example, at this diagram where you have the evolution of the coupling constant of the different interaction with respect to the energy scale, you would have around 10 to the 16th unification with just one single uh, uh, unified coupling here. And down this scale, you would need to break SU5 into the three different fundamental interaction described in the standard model, plus a breaking of the dielectric symmetry as we have seen before. So now, confronting this to experiment, there are theoretical prediction, of course, the unification of the coupling constant, and also the proton decay. Because in the proton, you can see in this Feynman diagram that if you exchange a leptoquark here, you can transform the proton into a positron and a pi zero. And so you can calculate the lifetime of the proton in your grand unified theory, and you'd find a prediction of 10 to the 28 to 30 years. And so people were very excited about this type of predictions, and they wanted to check that experimentally. Here, for example, you may know that the pi zero decays almost 100% to a pair of photons. And so people design an experiment where you would have lots of protons, for example, a big tank of water with walls covered with photomultipliers that could measure and identify the photons coming from pi zero decay. And this was, for example, Kamiokande and Super Kamiokande experiment in Japan. But then these experiments were conducted, and finally they since they didn't see this type of decay, they impose a lower bound on the lifetime of the proton, which is a few orders of magnitude larger than the maximum value it could take in a simple SU5 theory. Also, if you take all the beta function for the evolution of the coupling constant, and you take just in terms of particle content, the content of the standard model, you extrapolate, you will find that these coupling constants actually um, do not converge to a single value. And because of these different predictions that were not uh, verified in experiment, this simple SU5 extension of the standard model is there. Now, if we discuss what open problems grand unified theory could solve, so the unification of all quantum field theory of interaction of elementary particles like electroweak and strong interactions, a unification of quarks and leptons, because you can see that these two type of fermions can sit in the same representation of the group. You have an explanation for the quantization of the electric charge. You also have an explanation to avoid the Landau pole in the evolution of essentially the electromagnetic coupling constant. And in some larger grand unified theory, you also have an explanation for the neutrino mass. And the phenomena that they would predict is very heavy leptoquarks and possibly, which I did not describe, magnetic monopoles. Now let's move to supersymmetry. So supersymmetry is a symmetry between bosons and fermions. It's introduced via this fermionic operator Q here, which has a spin 1/2. And then if you apply it to a state with spin S, it will shift the spin by alpha unit in H bar. And so applied to a boson, it will give a fermion and vice versa. There are theory with global or local supersymmetry, and they might have 4 to 8 different SUSY generator, depending on whether they are global or local. However, realistic TV scale supersymmetry models must have a number of supersymmetry generator just equal to 1, because these are the only one where you can have a chiral representation. And so in your model building, you can, for example, have models with extended supersymmetry at some high energy scale, but eventually they will need to break down to just n equals 1 supersymmetry at the TV scale. For a long time, extension of the standard model in terms of supersymmetry was thought to be impossible because of the Coleman-Mandula no-go theorem, which states that any non-trivial union of the Poincaré, so space-time symmetry, and internal groups leads to an S matrix equals to identity. And this holds for all quantum field theory described with Lie algebra only, so only commutation relation. It means that essentially internal quantum symmetries don't speak to space and time symmetry. They simply commute with each other and have no type of relation. This was circumvented by Aix-Marseille and Lopezonsky, which realized that if you have an extension of the Lie algebra, if you want, some commutation relation, but also anti-commutation relations, then it's possible to have a non-trivial combination of a Poincaré group and internal symmetries. And if you look at the algebra of the supersymmetric extension of the Poincaré group, you will find these commutation relation and also these anti-commutation relations. Now, if you look again at Casimir operators, those who commute with all of these generators, you would find that P squared is still a good Casimir operator, whereas the square of the Pauli-Lubansky vector is no longer, because this SUSY generator has also is a fermionic operator. And so in terms of invariance, mass would still be a good invariant of an exact supersymmetry, but in super multiplets, which are multiplets where you have particle and their SUSY partners, you would have particle of same mass, but of different spins. Local SUSY is called supergravity because it automatically contains general relativity. And we can see that with this anti-commutation relation. When you apply two consecutive supersymmetric transformation, this is equivalent to translation in space and time, because P mu is the generator of the translation. It means that if you have a system which is invariant under supersymmetry, especially under local supersymmetry, it is also invariant with respect to local translation in space and time. And local translation in space and time is also an invariant with respect to a change of coordinates. And we have seen that this is the basis of general relativity. And so this is an interesting feature of local supersymmetry. Now, the question is, is this realized in the standard model? And of course, the answer is no, because if you count the number of degrees of freedom in the standard model, you would find many more fermionic degrees of freedom than bosonic ones. So this does not apply. And therefore, if you want to have a supersymmetric extension of the standard model, you need to double the mass spectrum of the standard model. And you can do that in different supermultiplets. For example, to fermions which have a spin 1/2, you can associate scalar fermions with a spin 0. And to the spin 0 field in the standard model, you can associate spin 1/2 exynos. In the vector supermultiplets, you would associate gauge boson in the standard model with spin 1 to gauginos, or spin 1/2. And in local supersymmetry only, you would associate the graviton of spin 2 with a gravitino of spin 3/2. Supersymmetry, if it's realized in nature, is necessarily broken. Otherwise, we would have found a selectron with the same mass as the electron. Remember that p squared is a Casimir operator, but with different spins. And so the selectron do not obey Pauli-Dirac statistic, they obey Bose-Einstein statistics. And then you would have strange atoms or molecules where the number of selectron in the orbitals would not be limited to 2. You could have really plenty of them, and this would make very strange properties in terms of energy levels of electrons in atoms or molecule. And this has, of course, never been observed. So we think that supersymmetry is broken, and that if they exist, we haven't seen these selectron yet, because their mass is much larger than that of the electrons. If you want to construct supersymmetric extension, a minimal supersymmetric extension of the standard model, you need in the Lagrangian to have one part which is globally supersymmetric here in this Lagrangian. It includes the Lagrangian of the standard model, which is invariant with respect to its gauge group. It associates standard model particle and their superpartners. In this part, electroweak symmetry breaking generates mass for standard model particle. This is renormalizable. And then you have different type of interaction between standard model and SUSY particles. But then, since you need to break supersymmetry, and we don't have a full model of this, what is done is simply to parameterize the effect of supersymmetry breaking by introducing explicit terms in this soft SUSY breaking part of the Lagrangian that explicitly violate supersymmetry, however, without reintroducing quadratic divergences. And this would explain the mass of the SUSY particle, which are mostly due to the breaking of supersymmetry. Here, for example, you have the detail of such as soft breaking supersymmetry with different parameters here, like this M3 that corresponds to the mass of the gluinos. You have, for example, the mass of the leptons which appear here, etc. In the MSSM, by definition, you just have one SUSY generator. The gauge group is the same as the standard model, and this is just a choice in phenomenology, since we so far we haven't seen additional fundamental interactions. You need two Higgs doublets instead of one in the standard model. And since the SUSY partner of these Higgs fields are Higgs-Zenos with spin 1/2, exactly like the fermion in the standard model, these Higgs-Zenos could contribute to anomalies, and you cancel the anomalies, setting up the weak hypercharge of these two Higgs doublets opposite. So this way you ensure that all the contributions of the corresponding Higgs-Zenos will cancel out. And so here, by introducing two doublets of SU2 left, you have in total 8 degrees of freedom. After the electroweak symmetry breaking, 3 of these will give a mass to W plus, W minus, and Z. And so you're left with 5 physical Higgs bosons, which are 3 neutrals here, a light scalar, a heavy scalar, a pseudoscalar, and 2 charge. With their partners here, which are these different Higgs-Zenos. The quarks are associated with scalar quarks, and the gluons are associated with gluino, etc. And you have a mixing in the chargino sector and neutralino sectors. The charginos are made of the partners of the Higgs, charge Higgs and the W partners, and the neutralinos are made of linear combination of the partners of the electroweak gauginos and neutral Higgs-Zenos. In the MSSM, we introduce a new quantum number, which is called R parity, defined like this: -1 to the power L plus 2s plus 3b, where L is the lepton number, S is the spin, and B the baryon number. This R parity is valued 1 plus 1 for the standard model particle and -1 for SUSY particle. And if it's conserved, it prevents having possible rapid decay of the proton, because you can see that here, if you would have this type of lambda 2 or lambda prime prime or lambda prime operators, we could also decay a proton into a positron and a pi zero, for example. If our parity is conserved, then SUSY particle are pair produced, and the lightest one, which appears at the end of each SUSY decay chain, is stable because it has no lighter SUSY particle to decay to. Often this lightest supersymmetric particle is the lightest neutralino. It has a mass due essentially to the SUSY breaking, so it's a massive particle. It's stable due to conservation of R parity. It has no electric or color charge, and therefore it interacts only via weak and gravitational interaction, making it a very good candidate for dark matter. In the standard minimal extension of the standard model in supersymmetry, you have a relation where when you calculate at 3 level the masses of the Higgs boson, which says that the lightest scalar Higgs must be lighter than the Z boson. But this is corrected by large quantum correction. And for example, at one loop, you have correction of this size, where MS here is the SUSY scale. But even if you play with all the possible parameters in the model, if you do a scan, you'd find that there is an upper bound to this lightest Higgs when you include the radiative corrections coming from the stop and the stop loop, something lower than 136 GeV. And so this is a prediction in the SUSY model. Now, how supersymmetry can answer to an open question of the standard model? It's a possible non-trivial extension of the Poincaré group. We have seen in the Aix-Marseille and Lopushansky theorem. It has a candidate for cold dark matter, for example, the lightest neutralino. When you include the SUSY particle around the TeV scale, their contributions to the loop will change the beta function of the three coupling constant. And because of this, you can get a unification of these at the grand unification scale. It has the inherently the prospect for a quantum theory of gravity, because the local supersymmetry incorporates general relativity. And then there is also radiative breaking of the electroweak symmetry. If you remember, in the standard model, we introduced a potential for the Higgs boson, which was mu squared times phi squared plus lambda phi to the 4. And the mu squared in the standard model was just set negative by hand, just to form this Mexican hat potential. Now, here we have two Higgs doublets, and there is one which couples essentially to the up quarks, and the other one to the down quarks and the leptons. The one which couples to the top quarks is driven negative at the electroweak scale just by the renormalization of the theory. It's essentially the non-compensation between the top and the stop loops that drives this negative, and the mass squared associated with this boson plays exactly the role of the negative mu squared that we introduced in the standard model. And here it's really the dynamics of the model that explains the electroweak supersymmetry breaking rather than just adjusting its parameters by hand. And also because of the supersymmetry, all the loop in the standard model that was generating these, for example, one loop corrections here are compensated by the super partner or this fermion here with this type of contribution to the loop. And if the supersymmetry is exact, then the mass of this fermion and its super partner are equal, and also their couplings here are related. And if so, there will be a perfect compensation between these quantum correction to the Higgs mass. And so, as we know, supersymmetry is broken, so we don't have exact compensation for this. But as long as the difference in mass between these is of the order of a TeV scale, then we manage to keep the Higgs boson mass at the electroweak scale. So supersymmetry is really reducing, if you will, the problem of the quantum corrections, and can really stabilize the Higgs boson mass, avoiding the fine tuning that you need to put in the standard model in presence of possibly high energy scale. If you look at also at precision measurement of the different electroweak observables, you find that supersymmetry, the MSSM, is still compatible with the data, and especially if you project that to the correlation between the W and Z mass, you can see that the central value here is compatible with supersymmetry. So in summary, what does it solve? So possibly the hierarchy problem, provided that the superpartners are not too heavy. It can also uh, have the gauge coupling unification in a supersymmetric version. If you conserve our parity, you can have a stable proton. You can have a good candidate for cold dark matter, for example, with the lightest neutralino. With the compensation between bosonic and fermionic contribution to the loops, you can stabilize the Higgs mass in the presence of a high energy fundamental scale. You have somehow a unification between fermions and bosons through supersymmetry itself. There are a few cases of finite quantum field theory, like for example, n equal 4 SUSY models. And there is a possible framework for a quantum theory of gravity based upon supergravity. It predicts, depending on whether you suppose supersymmetry is realized at the TeV or the Planck scale, additional Higgs bosons, the doubling of the rest of the mass spectrum of the standard model. So lots of new SUSY particle, a candidate for dark matter, and some modification of the quantum correction with respect to the standard model. And this can be searched for indirectly, for example, in Physicist or in the G-2 of the muon. And then I will finish with just a quick introduction to superstring. So there is no finalized theory of superstring, but rather a somewhat promising theoretical framework. The fundamental physics subjects in this theory are extremely tiny strings, open or closed, whose proper vibrating modes corresponds to the elementary particles that we know. So here in this drawing, you have an open or closed strings with their vibrating modes, which corresponds to the actual particles that we see. And for example, you have a generalization of the Feynman diagram with this type of, for example, closed strings here. In order to avoid having tachyons, these are particles with squared mass negative. In supersymmetry, in superstring theory, you need to include supersymmetry. And it's the only known theory with finite quantum gravity. The quantification of these type of symmetry requires to have extra spatial dimension, 6 at least. And we retrieve at low energy the 4-dimensional theory by the compactification of these extra dimension on very special manifold, which I called Calabi-Yau manifold. There are, of course, problems with this theory. There is a gigantic number of possible different manifolds, and not known criteria to choose amongst them. So it means that you might have, a gigantic number of realization of this theory, and you don't know which one to pick to try to reproduce the standard model, for example. And also it's difficult in this framework to interpret dark energy. Over the 1980s and 1990s, several superstring theory have been discovered, and Edward Witten found that they are all special limit of a common M theory. And in these M theories, the fundamental objects are not no longer vibrating strings, but rather vibrating membranes. And here you have a sketch of these M theory with different low energy approximation, low energy limits, which are either 11-dimensional supergravity or different type 1 or type 2 strings or heterotic strings. And these are all related with by some dualities. For example, the S dualities will establish some symmetry between strong and weak couplings between these different theories. The T duality will establish a symmetry between string along the radius of an extra dimension over the string along 1 over this radius, etc. And here in this table, I just try to summarize the main features of the different string theories. The first one was the historic first string theory that was initially introduced to try to explain the strong interactions. These has 26 space and time dimension, but it contains no fermions and has tachyons. The other, as you can see, include supersymmetry, and they are mostly closed strings in 10 space and time dimension. Some of them have a gauge group, like for example SO32, so very large gauge group, or E8 times E8. E8 are the exceptional symmetry group. And the best hope is this theory of heterotic strings, E8 times E8. And all of these type 2 or heterotic string have a graviton and no tachyons. Okay, and so just to finish, what the open problem could superstring theory possibly solve? Well, the unification of all type of particle into fundamental objects that are just vibrating strings or membranes. It's essentially a theory with no free parameter at the fundamental level. It could give a finite quantum theory of gravity and unification of with the other fundamental interactions. The new thing that it would predict is either supersymmetry at the TeV or maybe at just at the Planck scale. Some extra dimension, but if they are of the size of the typical Planck length, they would be extremely difficult to test experimentally. And for example, in some models, you have other predictions like axions that are testable in astrophysics experiment. Okay, that's all I have for these lectures. So I don't know if you have questions.
Yeah, actually, thank you for your lecture, but it's quite lots of information actually. Yeah.
Yeah, that's right. Yeah.
Yeah, I just have one question about the, for example, for the 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 we know about for fermion we have the direct equation, and 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 why, I mean, from which ideas we can build the Lagrangian for the, I mean, the direct Lagrangian.
Excuse me. I will try to go to this slide. So you're talking about the Dirac equation and the Dirac Lagrangian, right?
Yes, yes.
Yeah. So for example, this typically is a type of Lagrangian that you have for fermions like electrons or quark. So
Yeah.
if you want to introduce, for example, a model with an electron or a quark, these are the type of Lagrangian that would correspond to this particle.
But I mean, my question is that, okay, here you are
Excuse me,
so
the sound is not very good, so I will just try to um, not to use the microphone. Can you speak now?
yes, can you
Okay.
hear me? Okay.
Yeah, it's better now.
Yeah, I just my question is about the, I mean, here you show me one, I mean, the one equation for, I mean, one form of the Lagrangian,
Yes.
and I just wonder that, do we have the, I mean, is it possible to have another, I mean, another form for the Lagrangian of the fermion? I mean, or
So this is of course here what I've shown is only the Lagrangian for a free fermion, right? For
yes,
example, an electron sitting in no external field. And for this, no, there is no other type of equation. It's just for all the spin 1/2 particle of matter, you would get a contribution like this. And then, of course, if you include an EM field or weak interactions, then you will have, for example, the covariant derivative of this type of thing, where you would have interaction between the gauge boson of these, for example, like the W or the Z or whatever, that will interact with the electron. And then if you want to explain the mass of the electron, of course, you would need to have it interact with the Higgs field.
okay, thank you, I see. Yeah.
I don't know if you have other questions or remarks.
Um, okay. Actually, for the moment, I think I don't have any or other questions. So yeah, sure. I mean, but for me, is a, I mean, very detailed lecture. But could just one question. I mean, one informal question. Could you share the slide, or is private for only the school?
No. Of course, I will send you
Ah,
the PDF of this.
yes, yeah. Okay, that's right. Yeah. Okay.
Okay, I think I will stop the recording now, and so thank you for your attention, and
Yeah.
I hope that you have learned a few things in this lecture.
Uh,
I
okay.
guess
Thank
there
you.
are things that you already knew and maybe other information.
Yeah, yeah, especially for the information about, for example, extra dimension or grand unified theory. Yeah, I know a bit more about this. Yeah, thank you.
Okay. Okay, good.
Yeah.
Okay, I'm just stopping the recording now.